Hi, welcome to the sixth video of the system design series. In this video, we will talk about high-level trade-offs. In my opinion, this is one of the most important topics to understand when it comes to system design. So you should have a clear understanding of these trade-offs. So what is a trade-off? As per the definition, trade-off is a situation in which one attribute of a system or product is made less usable because another attribute has been given more priority. So what it means is like if we have two options, we have to prioritize one option over the other because we have some reasons. We cannot keep both the options along. We'll have to decide between one of them. So the three trade-offs in system design we have are performance and scalability, latency versus throughput, and availability versus consistency. So the trade-off says that either we can choose performance or we can choose scalability. So we cannot have both of these factors together after a certain point of time. Same with latency and throughput and availability and consistency. So let's understand each of them one by one. Performance versus scalability. So what is performance? Performance refers to the speed and effectiveness of a system under a given workload within a given time frame. So it says that to measure the performance of a system, we provide load to the system and monitor it to see how fast it completes the task. So the faster the task is completed, better is the performance of the system, right? Okay. So the next few lines which I'm about to say are very crucial. So please listen to that carefully. So for any system, we expect it to complete a given amount of work within an expected and reasonable time. If a system is able to do it, its performance is good, and if not, we need to do something to fix it. The faster a system is able to do it, the better the system is. So we know that. So consider the example of sorting. We know that a sorting algorithm takes O of n log n time. But if it is taking O of n square, we need to fix it, right? So performance is a software quality metric. It measures how well a software can perform its task. So this was all about performance. What is scalability? So scalability, as we have learned in our previous videos, it refers to the characteristic of a system to increase performance by adding additional resources. So let's say we have a task. It takes 5 seconds to complete it because it has very old processors, very less amount of RAM, and that too of lower frequency. Now, if you want to increase the performance of the system, what we can do, we can give it a better processor, we can give it a better RAM, and the performance of the system is likely to increase. Now, like if you see, there is a difference between performance and scalability. So they are not the same things. The performance is a software quality metric to measure the speed at which a task is completed, and scalability says that by adding resources we can increase the performance. So where does this trade-off come into picture? So before moving further, I hope you now have a clear understanding of these terms because this clear understanding will help you understand the trade-offs properly. If not, please rewind or watch a scalability video again. Let us understand this trade-off with the help of a supermarket analogy. So in this case, we have a cashier and we have a shopper. So the cashier can check out one shopper every minute. So if you see the performance of the cashier is one customer per minute. Now, let's assume case first in which one shopper comes and he wants to shop. So the shopper will spend one time for his order and for his cart to process. So the average performance of this in this case is 1 minute. Now let's say two shoppers come together. We have one cashier. So for shopper number one, it will take 1 minute. But for shopper number two, like he will have to wait for 1 minute for shopper number one to get completed, and then it will take another minute for the order for shopper number two cards to be processed. So if you see, for shopper number one, it took 1 minute, and for shopper number two, it took 2 minutes. So 1 plus 2 equal to 3. Now in this case, the average performance of the system got increased to 1.5 minutes, right? Because the number of customers increased. Now assume this situation. While the second customer was getting his task processed, number three and number four also came. So what will be the waiting time for customer three? So he will have to wait for 1 minute while customer two gets his card processed, and then he'll have to wait for another minute to get his card processed. So for customer three, it is 2 minutes, and similarly for customer four, he will have to wait for 2 minutes for 2 and 3 and 1 minute for himself, so 3 minutes. So total time for this system is 1, 2 and 3. So 1 plus 2, 3, 3 plus 3, 6. So 6 minutes. So this total waiting time will be 6 minutes. So if you observe one thing, so here in this case it was 1 minute, then it became 1.5 minutes. Now in this case total is 6 divided by 3, so it became 2 minutes. As we are increasing the number of customers, our graph is going down. So you can consider a scale with the number of customers that we have currently, and on the y-axis we have the performance. So as the number of customers are increasing, the average performance of our system is increasing because the number of time it is taking, the average time, basically we are concerned with average time. We are not concerned with the time cashier is taking to process one customer. We are concerned with the overall performance of the system, right? So, sorry, yeah. Yeah, so as the number of customers are increasing, the performance of the system is slowly decreasing, and this is not a good sign. And this is exactly where scalability comes in. Scalability is making sure that the performance is constant no matter how many people are coming in. So if you see, this is the graph, this orange graph, when we introduce scalability, it does tilt a little, but it's not that much as compared to when there is no scalability added. So this was the importance of scalability. Now, to increase the performance of a system, we also consider caching, right? So there's we prefer that we know that if we add cache, the performance can increase. So let's consider that scenario as well in our example. So in the supermarket, how can we add caching? So consider this example. They are customers who purchase bread and butter every day. So what the cashier can do, he can keep packets of this bread and butter ready, and whenever the customer comes, he can show his shopping list, and the cashier can immediately give him bread and butter. So let's say this process takes 10 seconds. The time taken per customer has reduced from 1 minute to 10 seconds. Who wants to purchase only bread and butter? But this system can fail for a number of reasons. The shopper is not consistent with what they buy. So let's say they can buy bread and butter, but what if they decide to add another item? What, right? So in that case, our system fails. So like whenever the customer hands over the receipt, it will take 10 seconds for the cashier to process it. But now after seeing the receipt, he got to know that, okay, he is not going to purchase only bread and butter. He wants other items as well. Now, those 10 seconds are already wasted. And now the cashier will have to spend 1 minute more on that customer. So because of that, it took 1 minute and 10 seconds per customer. So that increased the time. The second case can be the receipt data is lost, and this is called cache miss. So in this case, what happened? The receipt that was given by the customer didn't work. So it took time to scan, but it didn't work, and now the card has to be scanned again. So anyways, in this case also, instead of 10 seconds, our cashier now spends 1 minute and 10 seconds to check out a shopper. So in case of cache miss or in case of order change, the average processing time will increase. So what are the other options that we can have? We can have multiple cashiers. So let's say we add 6 cashiers in our supermarket. Now, whenever a customer comes, he will have to spend 5 seconds to deciding which cashier he should go to. So that is also not good, right? So in that case, anyways, it will take 1 minute for any cashier to process his order. But now, 5 seconds are being spent by the customer to decide which cashier he should go to. But anyways, like we don't care too much about reducing the performance slightly when there are only a number of shoppers. So basically what it says is, for a very few number of customers, we are not concerned if the performance increases, like if the time taken increases a little. But if the number of customers are more, in that case, it will surely optimize our system, adding multiple cashiers. Now, what will happen? Let's say we have multiple cashiers. There can always be a situation when the number of customers are more than the number of cashiers, right? So in that case, what will happen? Customers will start lining up behind cashiers. Now let's assume you are in one of the lines, and the person in front of you is taking longer, and the lines next to you are moving. So that will give you a sense of frustration, right? How to solve this? The answer of this problem can be similar to message queues. So in this case, what happens? Whenever a customer comes, he forms a queue. The queue is not in front of any cashier, but a general queue. Now, the customer who comes first is processed first. So like in this case, let's say we have 4 cashiers. Whenever this customer comes, he will be sent to the next available cashier. So whichever cashier gets free, the customer will be sent to that cashier. So in that case, our problem is solved. The person who comes first will be processed first, and he won't get frustrated seeing other lines moving. So like I said, this example is analogous to message queues. So we have message and we have our worker. So worker you can refer to as our processes, and these are the tasks sent by the user. So whenever any of these process gets free from the message queue, the first task is assigned to the worker. So basically, this is all about performance. and scalability. So, if you have a performance problem, your system is slow for a single user. But if you have a scalability problem, your system is fast for a single user, but slow under heavy load. And this is exactly what we observed in our graph. So when there were only one or two users, the performance was relatively more. But as the number of users kept on increasing, our graph was going down. And that's exactly what is explained here. So till now we got to know about performance and scalability, but where is the trade-off? So understand it this way: a service is scalable if it results in increased performance in a manner proportional to the resources added. So this says that when we add more resources, the performance of a system increases. But now let's say our application has been there for a long period of time. As the time increases, more data gets added to the system, right? Now, for simple search operation, which takes n log n time, if the value of n is less, it will obviously take less time. But as the time passes, more data gets added to it. The value of n increases. So the value of n log n also increases. That means our complexity is still the same. The time complexity remains same. But because the number of data has increased, it will take more time to process the same data to get a result, right? So that's where the trade-off comes. Like after some point of time, if you add more resources to scale your system, you won't be able to handle more number of customers. You only will be able to increase the time it takes per customer, right? Let me repeat. So let's say one customer, our store gets very big. Like there are thousand, like a number of items in the store. Earlier it was taking 1 minute, but as we added more items, it will take longer to search an item and then add it to the cart, right? So let's say now it starts taking 2 minutes, 2 minutes per customer, right? Now, if you want to scale your system, you will add more resources to it, and you will add resources in such a way that it reduces the time it takes per customer to increase the overall performance of your system. And this is the trade-off between performance and scalability. I hope I made that clear. That after some point of time, you cannot handle. You only can optimize your system when you add more resources to it. You won't be able to handle more number of users. Next up, we have latency versus throughput. So what is latency? As per the definition, latency is the time required to perform some action or to produce some result. And it is measured in terms of time, like hours, minutes, seconds, nanoseconds, or clock period. So for example, let's say you want to send a message to your friend from point A to point B. And it takes 100 milliseconds to send a message. So the latency of that message is 100 milliseconds. And if you increase the distance to which that message has to be sent, it will take longer. So for example, if you're sending a mail, right? So if the person stays near to your place, the mail will be delivered quickly. But if he stays in some other country, it will take longer to deliver that mail. So that's exactly what latency is. Throughput is the number of such actions executed or results produced per unit of time. So consider the example of message again. So we know that one message will take 100 milliseconds. Now if you want to see how many messages can we send in 1 second, so that will be 10 messages, right? So that's the difference between latency and throughput. In latency, we see how much time a task is going to take, and in throughput, we fix the time. We monitor for a fixed period of time and we see how many tasks are getting completed within that time. Like I explained with the example of message. So 100 milliseconds is the latency, and 10 messages per second is the throughput. This is measured in units of whatever is being produced: cars, motorcycles, IO samples, memory words, iterations. It can be anything. So the term memory bandwidth is also sometimes used to specify the throughput of memory systems. Let's say you're downloading a system and we are getting a speed of 100 megabits per second. So the throughput is 100 megabits per second. So you're observing for 1 second, and you are observing that you are able to download 100 megabits. So that's the throughput. Now let's understand this trade-off with the help of an example. Suppose we have a service that solves mathematical equations, and there are two kinds of users using a service. So first type of users who use a service casually, and second type of users who use the service in bulk. So let's say a user comes and gives one equation and he gets the result. So what he is concerned with, he wants the result as fast as possible. So that is the on-spot user. So like he comes not very often. But whenever he comes, he has one or two equations, and he wants the system to solve that equation as quickly as possible. So he is concerned with latency. On the other hand, we have bulk users. So what they do, they give a huge data set and which consists of a lot of equation. He's not bothered with latency, rather only the throughput. Okay. A system can have limited processors, right? So what user 2 will want? He will want that all the processors are always occupied and they are computing his data set. So what the bulk user wants? He wants maximum throughput. He wants maximum number of outputs within a given time frame. But if all the processors are occupied solving the task of the bulk user, it will become problematic for the casual user, right? Now he will have to wait until some processor gets free and gets his task done. So this will be beneficial for the user 2, but it will be problematic for user 1. What can be a solution? One solution could be splitting our cluster into two different clusters. One which will have low latency, another that will have high throughput. So in our front end, we can give option to the user which cluster he wants to use. So with low latency one, casual users like one or two persons who have to solve one or two equations can come. Or we can do this automatically also. So based on the input file given by the user, we can see how many equations are there, and based on that we can redirect the problem to the correct cluster. So this way, the user will have much clearer expectation about the performance and the scaling characteristics of our service. So generally, we should aim for maximal throughput with acceptable latency. And lastly, we have availability versus consistency. So this covers CAP theorem and availability patterns. And we have talked about all of these topics in depth in our previous two videos. So if you have not watched them, I request you to watch them to get a better understanding of this trade-off. So that was all as part of this video. Thank you for watching. I hope you learned something new.